All right, let's finish up the handout from today. We had this integral here to complete. Now, we do have a composition of functions in the numerator here, right? We have one function inside another function, and so you might expect to use u substitution here, just like we did for number 12. And that would work out, except we would need we'd need logarithms to sort of finish it off, and we haven't talked about those yet. So instead of doing that, let's just try and simplify the numerator a little bit and see what happens. All right. So if we expand it out, we get 1 squared, which is 1, plus 2 times 1 times e to the x, and plus e to the x quantity squared, all over e to the x. And now we can split this up into 3 fractions, right? 1 over e to the x is also known as e to the negative x. 2e to the x over e to the x. The e to the x is canceled, we just get 2. And then e to the x squared over e to the x, we can cancel one of those e to the x's, and we have an e to the x left in the numerator. And so we need to take the integral of that. Now, that first one is going to require a little bit more work. Okay, but the integral of 2 is just 2x, and the integral of e to the x is just e to the x. Okay, and we'll add on any constant capital C. All right, now to finish this one up, I am going to use u substitution for this. I have this sort of inside function negative x up in the exponent there, so we will do u equals negative x, and du equals, the derivative of negative x is negative 1 dx, and that means that just multiply both sides by negative 1. Dx is negative 1 times du, right? So if I rewrite this in terms of u, I get, let's just focus on this for a moment. We'll bring that back at the end. Okay, so this is going to be the integral of e to the u, and then the dx becomes a negative du. Let me put the minus sign out front here. Okay, and the antiderivative of e to the u is e to the u. So this is negative e to the u. And then we can put it back in terms of x by replacing u by negative x. So we get negative e to the negative x. Okay. Oop, disappear minus sign. Come back here. Okay. So antiderivative of e to the negative x is negative e to the negative x. And that works because if you were to take the derivative of this using the chain rule, then you'd get another minus sign, which would cancel this one. And so you'd end up with what you want. All right, so putting all that together, this becomes negative e to the negative x plus 2x plus e to the x plus an arbitrary constant c. And that's our answer. Now, since we're chatting, let's go ahead and look at these fun facts about e on the next page. Just tell you a little bit about these. These are some interesting sort of math cultural knowledge to know about. If you heard about e in the past, you probably heard about it in the context of continuously compounded interest. Okay, so think if you had $1 and you invest it for 1 year and did it at 100% interest, then without any compounding, you would have how much at the end of the year? You have total of $2, right? You have your original $1 plus another $1 to added to it, so you'd have 2. But if you start compounding the interest, where you sort of get interest at multiple times over the year, and then you start earning interest on your interest, you're going to end up with more than $2 at the end of the year. And if you sort of take that process to its logical conclusion and you compound continuously, then you're actually going to end up with E dollars at the end of the year. 2.71828 ... dollars. Okay, so that is an important place where E shows up in the world of finance. Here's a great one. E is equal to the, whoa, how'd that happen? I don't know. The sum of the reciprocals of factorials. I wonder if I can fix that somehow. Maybe? No. Well, you can still see it. So it's 1 over 1 plus 1 over 1 plus 1/2 plus 1/6 plus 1/24 and so on. And that all adds up to E. And well, by the time we get to the last chapter of Calc 2, you'll understand exactly where this formula comes from when we talk about Taylor series. Okay. All right, here's my favorite one, the asymptotic probability of derangement. Not that kind of derangement. Derangement here means sort of mixing up the order of things and making sure that nothing ends up where it started. Okay, so E is the reciprocal of the probability that when infinitely many people trade hats at random, nobody ends up with their own hat. All right. So if you think about it, if you have 3 people and they trade hats randomly, then I think there's a 50% chance that nobody's going to end up with their own hat. Okay, so 1 over 0.5 would be 2. All right. But again, you could look at what happens with 4 people, with 5 people, with 6 people, and it becomes a little bit less likely that nobody will end up with their own hat. Okay. In other words, this denominator becomes a little bit smaller, and in the limit, as the number of people approaches infinity, the probability is going to approach 1 over E, and therefore its reciprocal will approach E. All right, so that's kind of crazy. E is the right limit, or I don't know, you might call it the upper limit, I suppose, of this integral. Oh, it did a dance again. And this integral, as you know, means you're looking at the graph of 1 over t, which the right half of that graph looks like that. Of course, you have another part over here in the third quadrant. And if you're going to start, well, you're going to start here at 1. And then you want to go over far enough such that you have an area of exactly 1 under the graph, right? You want the area to equal 1. Then turns out you have to go up to E on the x-axis to make that happen. Here is probably the most famous formula in mathematics. E to the I pi plus 1 equals 0. And famous because it sort of shows how maybe the 5 most important numbers in mathematics are related to one another, right? You have pi, which is the ratio of the circumference of a circle to its diameter. It comes from geometry. You have I, which is the square root of -1. It comes from algebra. You have E, which comes from calculus, right? And then 0 and 1, well, those are pretty important. So what does this mean? I mean, this is really, this is something you might learn about in a complex analysis class as a junior or a senior, but I can draw a picture which sort of describes it. E to the I pi, this is the complex plane, and so like 2 plus 3 times, the square root of -1, you'd represent as the point, 1, 2, 1, 2, 3. Okay, so this is called the real axis. This is the imaginary axis, and my formula is hiding again. And okay, so basically every complex number can be represented as a point in this plane, and e to the I times any angle is going to be some well, let me get rid of that picture real quick. E to the I times any angle. Oh, now they don't want me to draw. All right, we'll figure this out. E to the I times any angle, basically what you do is you travel that angle around the unit circle, and then you stop. And if the angle is pi, that's 180 degrees, and so you stop over here, and that is, it's the point -1, 0, but that means -1 plus 0 times I times the square root of -1, and that's just -1, right? Well, if you take negative, so this e to the I pi is -1. If you add 1 to that, you get 0, right? So this sort of geometrically means that if you travel halfway around a circle and then, kind of move one distance of 1 that way, you end up at the center of the circle at 0 plus 0i, namely at the number 0. Okay. You'll actually be able to prove this formula by the end of Calc 2 as well. Again, using Taylor series in the last chapter. All right, just a couple more. Stirling's formula is a crazy way to give the approximate value of n factorial, and you might think, why do I have to approximate n factorial? I can just compute it pretty easily. Well, these are all, say you wanted to know about how many digits 100 factorial had, right? It's not clear how to do that, but the right side here is expressed completely in terms of functions that are simpler than factorials, that you can get a handle on sort of how big the right side is much more easily than you can with the factorial. Okay, so that's a useful approximation. And finally, e can be represented as a continued fraction like this, and sort of a limiting process. And there's a pattern to the numbers here. These are all 1s on top, and then over here we have 1, 0, 1, 1, 2, 1, 1, 4, 1, 1. What do you think? 116. Okay, it's just the even numbers that sort of are interspersed with the ones here. So that's pretty bizarre. And this sort of encodes some of the deep structure of what this number E is all about. So, well, that's what I have to share with you. Be sure to go and listen to this wonderful E song some more and read through those lyrics to learn more about E. And that's it. I'll see you tomorrow.